In this video, we're going to look at Poisson processes and also the distribution, the Poisson distribution. All right, let's first define what a Poisson process is. Now, in Poisson processes, they're discrete events that are happening over a course of time. Now, let me give a couple examples. One of them might be like at a call center or something like that, where phone calls are coming in. And so I drew a line here where we've got a timeline, and each of these red X's is showing us when a call occurs, when a call comes in. So a call could be coming in at, or calls are coming in at different times during the day or whatever. Now, another thing that might happen is, if we're looking at decaying materials like uranium or something like that, if we're on a much shorter time scale than the half-life of the uranium or the material, then it sort of behaves this Poisson process. So these would be events of when atoms are decaying. And so, like if you've seen movies or something, or used a Geiger counter, each of those little pops or popping noises or blips on the Geiger counter are the decaying atoms. And so those are happening at specific points in time, and on a short period of time relative to the half-life, they kind of obey this Poisson process. All right, so we're looking at a period of time where these events are occurring, and if you look at this capital T here, what we're going to do is we want to find the probability of having K occurrences or events in that interval of time. So if we're starting here at 0 and we're going through this amount of time, we want to know what's the probability of having K occurrences in that amount of time. All right, the way we're going to sort of develop this is by breaking up this timeline into small segments. And so we'll assume that the small segment is delta t, and therefore if we count up the number of delta t intervals that we have from 0 to capital T, we know we can get that number by taking capital T and dividing by delta t. That'll tell us how many of those intervals we have in that time span. And so we'll call that little n, or lowercase n. So that's the number of intervals of size delta t that we have in that time span, capital T. All right, so we're going to want to find the probability of K events in that time span. Now, a Poisson process has these three following properties, and you either have to observe that these are true or kind of assume that they're true for the process. But if it is a process that is a Poisson process, it will have these three properties. The first one is that the probability of success in delta t is proportional to that time interval, delta t. So we'll assume that there's some other parameter, alpha, the Greek letter alpha, that we use to determine the probability of an event occurring in that time span, delta t. And so as that delta t would change, then the probability is going to change. So if delta t was smaller, then p would get smaller, or if delta t was bigger, p would be bigger. All right, so essentially that it's proportional to the amount of time that we're looking at. Now the second property is that the probability of having two events in this small delta t is negligible. So we'll look at probability of having one event occur will be that little p, and the probability of two events in that amount of time will just be negligible. It will be very, very small. All right, so the third property is that the probability of success in non-overlapping intervals are independent. So if we took a look at this interval and this interval here, the probability of, let's look at the second one, the probability of an event occurring here is independent of whether an event occurred in this previous one or in the next one or in any of the others. So they're all independent. So if you think of calls coming into a call center, each person that calls in is not really calling in dependent on when somebody else calls in. And so you would think of those as being independent. So the probability for what happens in one time span is not dependent on what happened in a different time span. So the probability of success in those non-overlapping intervals are independent. So they're all independent. All right, so just as a reminder or kind of pointing out something here, this alpha value here that we have here is the average number of successes per unit time. So based on, probability is a unitless quantity, and so if delta t has units of time, then alpha has to have the units of 1 over time, or the average number of successes per time. Okay, so that's what that alpha will be equal to. All right, so now let's look at the probability of finding those k successes in that time span capital T. Well, we know that the probability of success in each interval is that value p, which is alpha times delta t. We know there are n intervals, or n intervals that we're looking at, or n trials that we're going to be examining, and each interval is independent. So these are like independent trials that we're looking at. So if you remember from the Bernoulli trials, this kind of obeys Bernoulli trials, where we have n trials, which are the n intervals. The probability within each interval is p, and all of those trials are independent. So that kind of forms our Bernoulli trial. So if we have a Bernoulli trial, then the probability of k successes in that time interval t will be essentially the number or the probability of k successes in those n trials that we have. And so that'll be basically our binomial distribution. So we'll have n, choose k from n, p to the k, and q to the n minus k. So that'll be our probability. Now we could use this, probability and, do that calculation, but we don't know what delta t is, and we're kind of dealing with things that are continuous here. So what we're going to do is we're going to let delta t go to 0, and as delta t goes to 0, we know that, because n is equal to capital T over delta t, that n will go to infinity, and therefore as what we have to look at, what is n times p. N times p, we know p is alpha times delta t, which we had from up here, and n is capital T over delta t, and if we multiply this through, the delta t's cancel, so we get alpha times t, or this alpha times our time interval. Now it can be shown, and we kind of talked about approximating the binomial with a Poisson distribution in a different video, so the same kind of approximation can be shown here. But if we let lambda be equal to alpha times t, it can be shown that this binomial distribution will approach the Poisson distribution, where lambda is equal to alpha times t. Remember, alpha is our number of successes per unit time, and capital T has units time, so that'll become unitless. And so our probability of k successes, or k events occurring in our interval t, capital T, will be equal to lambda to the k e to the minus lambda over k factorial. And again, lambda will be this alpha times t. Okay, so let's look at an example to see what we're talking about. Now, let's suppose we've observed calls over time, and we've found that on average 3 calls arrive every half hour. Now, on average, the questions that we want to answer are, what's the probability no calls will come in an hour, or the probability that 2 calls will come in 15 minutes, or the probability that 3 or more calls will arrive between the time 11 o'clock and 11:45. Okay, so since we're dealing with events that are occurring over time, and we can assume that, and we're dealing with like a call center, we'll assume that this fits a Poisson process, and that we then need to figure out what is the lambda, and then we can do our calculations. So remember to find lambda, we need alpha times capital T. Alpha is a constant, and we know that alpha has the units of the number of events per unit time. And in this case, we're dealing with 3 calls. We said 3 calls arrive every half hour, and so that on average, and so that will give us our that information will give us our alpha that we need. So the other problems are dealing with different units, but we'll just put alpha in terms of hours. So we have 3 calls per half hour, so I put 1/2 hour, and that will end up being equal to 6 per hour, or essentially 6 calls or 6 events per hour. Now let's look at our probabilities that we want to calculate. The first one is that we want to know the probability of 0 calls in 1 hour. Well, the problem will let us know what capital T is. T in this case is 1 hour. And so we know that alpha is 6 per hour. T has the units of 1 or hour. So we'll let T be equal to 1 hour. And we multiply 6 over hours times 1 hour. Hours cancels, and we just get 6. So alpha is 6 in this case. And we want to know the number or the 0 events in 1 hour. So K is equal to 0. So our probability then will be equal to lambda to the 0, e to the minus lambda over 0 factorial. And that'll just be e to the minus 6, which is this really small number, 0.002479. Okay, now let's look at the next one. The next one, we want to know what's the probability of 2 calls coming in 15 minutes. All right, 15 minutes is not in the same units as alpha. Alpha is in hours, and so we need to convert this time interval into the same units that we had before, or that we have for alpha, so that when we multiply them, the units will cancel. So T is 15 minutes, or 1/4 hour. And so when we calculate lambda, lambda is alpha times T, which is 6 per hour times 1/4 hour, so hours cancels, and we get 6/4. So make sure that when you're calculating that calculating that lambda, that those units cancel correctly. Don't just put in, numbers here and assume that everything's fine, but make sure you've got the right units. So since alpha is equal to 6/4, and we want to know K equal to 2, we have alpha to the 2, e to the minus lambda over 2 factorial. So we've got 6/4 squared times 1/2, 2 factorial is just 2, e to the minus 6/4. And so that ends up being equal to 0.2510. Now the last question is, what's the probability of having more than 2 calls from 11 to 11:45? Okay, of course we're dealing with 45 minutes there, so the time interval that we're dealing with is 45 minutes. Again, we want to make sure that we have consistent units, so we're using hours up here. So we'll say T, our interval, is 3/4 of an hour, which is 45 minutes. So lambda will be 6 per hour times our 3/4 hour. The hours cancel, and we get 4.5. Now, since we're dealing with more than 2, meaning 3 and up, we can also say that that's equal to 1 minus 2 and below. And so we'll put in 0, 1, and 2 for our k's in this equation, and subtract that, that from 1. And therefore, when we do that calculation, we get 0.8264. So the probability of having more than 2 in 45 minutes is 0.8624.